Welcome back. Since last one or two classes, we have been discussing about chemical shifts. We understood why the chemical shift arise, what is the unit of measurement of chemical shift, for example, ppm, how to convert ppm to frequency, frequency to ppm, various important concepts we discussed. Today we'll continue further with the discussion on chemical shifts. Remember in the last class, we discussed about the conversion of ppm to frequency and vice versa. Just before continuing further, this being an important point, let us recapitulate with one or two slides about this conversion, process of conversion from ppm to frequency. Let us say on a 600 MHz NMR spectrometer, 15N is resonating at 60.8 MHz. That is true, right? We are looking at 600 MHz spectrometer. Gamma of nitrogen 15, as I have been telling you, is nearly 10 times smaller. So its resonating frequency is 60.8 MHz. Now my question is, what is 50 ppm when expressed in hertz in the 15N spectrum? So in the nitrogen 15 spectrum, what is 50 ppm on a 600 MHz spectrometer? That is my question. I'm sure we have been discussing so much, all of you would be in a position to answer this. In any case, let us calculate this one. All we have to do is, when you know the value in ppm, as I have been telling you, you have to multiply by the resonating frequency. Since the resonating frequency of nitrogen 15 is 60.8, simply multiply 50 into 60.8. So the 50 ppm in hertz in the nitrogen 15 spectrum is 30.4, 3040 hertz, 3040 hertz. Okay. What is 120 ppm? The same thing if I ask the question. Don't get confused. Now what you have to do? Simply multiply 60.8 by 120. This is the frequency. So logic is simple. Conversion from ppm to frequency, you have to multiply by the resonating frequency. So 330 ppm, if I just extend the logic, multiply by 60.8, it is 20,064 hertz. So this is the way we converted ppm to frequency. Now we will also do one reverse of it. In the sense, I'll convert frequency to ppm so that you will recapitulate everything before we proceed further. Now my question is, what is 11,000 hertz in ppm in the nitrogen 15 spectrum at 60.8 megahertz? Answer is, you have to divide the frequency by resonating frequency. So divide this value, divide this frequency in hertz by resonating frequency. So 11,000 divided by 60.8 turns out to be 180.92 ppm. Remember, so it is very easy. You understood how to convert frequency to ppm. Now what is 14,450 hertz in ppm in the same spectrometer for nitrogen 15? Of course, simple arithmetic. Now this conversion must be in your fingertips. I don't have to explain to you. Simply divide 14,450 by 60.8 and this is the value you are going to get, 237.66. Last example, same logic, 70,750. If you want to get the answer in ppm, take this value, resonating frequency is given as 60.8, divide by this, and this is the ppm value for nitrogen 15 in a 600 megahertz spectrometer. Okay, with this, I'm sure all of us would have become familiar by frequency to ppm and ppm to frequency conversion. This I have repeated many times. Several examples I gave just because it's a very, very important concept. Okay. Now let us continue further. So what we have to do is let us now use some common terminologies that normally used in understanding high field, low field concept, what is shielding, what is de-shielding, etc., which is commonly used in NMR. So what is that commonly used terminology? Take for example, Cl, C, H. It is a bond. Let us say CH bond is there, where for carbon, chlorine is attached. We all know the bond polarity, we can write this as delta minus and this is delta plus. The chlorine is being electronegative, it is going to withdraw charges from this carbon. It withdraw electrons. As we saw in one of the previous slide, if you look at the charge distribution pattern, see this is the shape you are going to get. A gray color shade, which it is written here, this is the charge distribution. Now as a consequence, CH bond is delta minus for carbon and delta plus for proton. This is what the conventional way we write about bond polarities. Now, with this, let us see what is happening for shielding of protons and where does it come. In a 0 to 10 ppm scale, remember I said proton spectrum comes more or less all the time in the region of 0 to 10 ppm. Now, in this case, proton is, because this is withdrawing electron, it is, let's say, de-shielded. Doesn't matter. Higher the de-shielding of the protons resonated lower field. Lower field means higher frequency. Don't get confused. These are the terminologies we use in NMR. So I want to make it very clear for you about the common terminologies what we use in NMR. This is the scale I have taken from 0 to 10 ppm. Now I go from left to right. Look, there is a spectrum, let's say, which has all the peaks running from 0 to 10 ppm in this range. If I start from the left side of the spectrum and move towards the right side, then the common terminologies what we use are, we are moving towards higher field. The peak comes here is at high field, then peak comes here. And the peak comes here is at lower field than the peak that comes here. So when you move towards the right, you are moving towards higher field. Or in other words, we say it is moving towards lower frequency. For example, I have a peak here. It is at, let us say, 500 hertz in the frequency. If I have a peak here, it will be 2500 hertz. As from the frequency scale, this is the higher. From the frequency scale, this side is lower. Higher the field, lower the frequency. And also, we say this side is lower ppm. Remember the scale here. This reference comes here. This is 0 ppm. Because this is 0 ppm, this is 10 ppm. When you go from left to right, what is happening? You are having lower ppm value for the peaks. Peak comes here maybe at 8 ppm. A peak which is coming here maybe at 1 ppm or 2 ppm. So the lower ppm when you go from left to right. Also it means it is higher shielding. If I say proton is highly shielded, it comes close to this side, layer 0 ppm or somewhere in this region. So if a peak is coming here, let us say chloroform is here, astronatal is here, let us say. That means the chloroform is less shielded than acetonitrile. So remember this point. As you go from left side to the right side of the spectrum, I'm covering the range from 0 to 10 ppm. But conventionally, the terminologies what we use in the regular NMR spectrum is we are moving towards high field, lower frequency, lower ppm, and higher shielding. These are the terminologies. What happens if we come from right to left? Everything is same, only thing things get reversed here. Now, from 0 ppm, if you come towards 10 ppm, you start reading the spectrum from right to left, then you are moving towards lower field, higher frequency, higher ppm, and higher de-shielding. Exactly reverse of what you read from going from left to right. So remember, if a peak is coming somewhere near 10 ppm, it is coming, we say the peak is coming at the lower field, or it is resonating at higher frequency compared to a peak which is coming here. Or I would say a peak is here, it is at higher ppm than peak here, which is at 1 or 2 ppm, which is much lower. The value is lower here in ppm. Similarly, if I say peak is here, this is more shielded than peak here, so this peak is less shielded. These are the common terminologies we use. Don't forget this. When you read the NMR spectrum, going from left to right, this is the nomenclature we utilize. These are the terminologies we always use: higher field, lower frequency, lower ppm, and higher shielding. Going from right to left is lower field, higher frequency, higher ppm, and higher de-shielding. Okay, this is a simple diagram to explain what happens when you go from right to left or left to right. Fantastic diagram. Please look at it. This is the bell. This is, let us say, the bell circumference is the charge distribution around the site of the nucleus. This nucleus, let us say this pin, is more shielded. See this, this is a circular shape here, the charge distribution. This circumference is much larger than this. This is much larger than this. Then like this it goes. So it means what happens is the charge distribution is, or I would say the shielding is becoming more and more as you go from left to right. This is a simple diagram to give you an idea how the shielding works. Okay, how do you read the spectrum going from left to right or right to left? How do you say which side is shielded, which side is de-shielded, or which side is higher ppm, lower ppm, higher frequency, lower frequency? All these terminologies. Okay, now chemical shift, does it depend on the field? Remember the equation, famous equation which we wrote: nu is equal to gamma into b naught over 2 pi. What does it mean? The resonating frequency varies linearly with the magnetic field. I explained this because gamma is constant, 2 is constant, pi is constant. So the resonating frequency linearly proportional to magnetic field. So that means higher the magnetic field, higher the resonating frequency. What is the meaning of that? When the resonating frequency becomes larger and larger, we explained conceptually, the energy separation becomes larger and larger, resolution becomes better, and spectral dispersion becomes better and better. What it means is, when you go to higher and higher magnetic field, remember, when you express in frequency, the spread is larger. That means larger the dispersion, better the resolution. Let us look at it very carefully now. I am going to, let us say, take a spectrum of proton at 200 megahertz, a proton spectrum of some molecule. Let us say I have recorded from 0 to 10 ppm. What did we understand so far? In expressed in ppm, this is 200 megahertz. I simply said you have to multiply the ppm value by the resonating frequency, that is 200 megahertz. So just not megahertz, don't consider the value megahertz, just multiply by 200. 10 ppm into 200 is 2000. Okay, when you multiply by the frequency, don't take into account 10 to the power of 6. Simply take the frequency, what is given in the number for resonating frequency, without taking 10 to the power of 6 term. Discard the 10 to the power of 6 term. Take only 10 into 200, it is 2000 hertz. That's what I was telling you in the last couple of slides. Let us say the same spectrum is taken at 400 megahertz spectrometer. What is 0 to 10 ppm here? 10 ppm, you have to simply multiply by 400 to express in hertz. So it become 4000 hertz. Now I'll go to 600 megahertz spectrometer. See the spread now. The spread is again multiply 10 by 6, 10 into 600, you get 6000 hertz. But what is happening in the ppm scale? Always I am maintaining the same scale, 0 to 10 ppm, 0 to 10 ppm, and 0 to 10 ppm. So in the ppm scale, when I express, it is not changing. 0 to 10 always remains. But when I go to higher and higher magnetic field, in the frequency scale, you can see there is a spread in the spectrum. This we call spectral dispersion. The spectrum gets more and more dispersed. More and more dispersed means better advantage for us. Let us take an example. If 10 peaks are in a small range, it is difficult to resolve and identify and make assignment. On the other hand, I spread it here. Then you have a better resolution. You can identify each peak very precisely and make the resonance assignments. A simple logic. I'll tell you, let us say there are 50 people crowded in a small room of 10 by 10. They are all standing. You do not know who is who. To identify is very difficult. Now, I'll ask them to come to the field, open field. All of them have to stand in a queue, giving some distance between them. Okay? All of them stand with 5 feet apart. Very easy for me to identify who is X, who is Y, who is Z. This is called dispersion or resolution. Remember, higher the magnetic field, we have better spectral dispersion, so the resolution is much better. So, now I will give you the comparison of chemical shooting frequency and ppm scales. Let us say I am starting from 200 megahertz to 800 megahertz. So what it means is I am varying the magnetic field. A different magnetic field strands by my resonance equation, nu is equal to gamma into b naught over 2 pi. I have different resonating frequencies. Okay, this means I have different spectrometers here. Going from bottom to top, magnetic field is increasing. I have different spectrometers. Consider the same 0 to 10 ppm scale. I am going to take the spectrum at 200 megahertz in the ppm scale. I have, let us say, 3 peaks. One is coming at 1 ppm, one is coming at 3 ppm, one peak is coming at 6 ppm. You understand? There are 3 peaks coming at 1, 3 and 6 ppm. Now, I have another spectrometer. I will go and record the spectrum at 400 megahertz and then get the peak positions in ppm are the same 3 peaks. What happens now? Remains same. This ppm, this peak which is at 1 ppm at 200 remains same at 400. This peak with 3 ppm remains same at 400 megahertz. Similarly, this peak at 6 ppm remains same at 400 megahertz. Go further. At 600 megahertz, higher frequency, that is better spectrometer, 600 megahertz spectrometer. See, when I plot in the ppm scale, it is not changing at all. The same 3 peaks always come at the same ppm values. Go to 800 megahertz, exactly same. So, when you express in the ppm scale here, spectrum, the chemical sheet values remains unaltered. Okay, always when you express in ppm, The peak positions in whatever the spectrometer frequency you measure remain same. Now, we'll go further. We'll go to the frequency scale now. What happens when I express in frequency? I'm converting ppm into hertz. So 1 ppm into 200 megahertz is 200. 3 ppm is 200 megahertz is 600 hertz. 6 ppm is 1200 hertz. I have been telling you how to convert ppm to frequency. I simply multiply by the resonating frequency, discarding the 10 to the power 6 term. That's all we have to do. Now same at 400 megahertz. What happens? 1 ppm is 400, 3 ppm is 1200, and 6 ppm is 2400. So you see, the spectrum is becoming more and more dispersed. As you see, they move apart. The peaks start moving apart. It appears as if they're distancing themselves. Go further. Same logic. At 600 megahertz, it is 600 hertz for 1 ppm, 1800 for 3 ppm, and 3600 hertz for 6 ppm. The spread is even better now. Go to 800 megahertz. You see, 800 is 1 ppm, 2400 hertz is 3 ppm, 4800 6 ppm. Now what is happening? The spectral dispersion become better and better. So when you express in the frequency scale, you will get better dispersion of the spectrum. Remember this point. Okay. I hope you understood this thing. When expressed in the ppm scale, spectrum remains same. Whatever the value you express in ppm in any spectrometer, that remains same. Whereas in the frequency scale, it increases. That shows there is a dispersion in the spectrum, giving better resolution. All these chemical shifts are the fingerprints of the molecule. Now I get a spectrum, let us say. I have a peak. Several peaks I am going to get. Now, I want to understand if there is a peak here, what does it say? If there is a peak here, what does it say? This is a picture taken from book of Bernard Plumage, where it says, see, for example, each frequency corresponds to a radio frequency, like if FM band, as I said, NMR comes in the radio frequency. Let us say it is one of the radio frequency corresponding to particular radio station. This peak corresponds to particular radio station. So that means each peak which is coming in different regions of the spectrum have some idea. We have some idea why, if it is coming here in a proton spectrum, this is because of particular functional group. Approximately, I mean, there can always be deviations. I'm not telling that if a peak comes here, this must be this functional group. Let us say a very high field, close to 1 ppm, if I get a peak, by and large we say it corresponds to more or less methyl region is there, methyl protons could be there. The same methyl proton, if you attach oxygen, it will come here, it becomes methoxy. So we have, depending upon where the peak comes, depending on the region, more or less people have classified different functional groups which are resonating at different frequencies of the NMR spectrum. This is why we can say NMR spectrum is like a fingerprint of the molecules. It's like fingerprints, like a radio frequency signal. If there is a frequency here, I know it is a Bangalore station. There is a frequency here, I know it is a Delhi station. There is a frequency here, I know it is a Mumbai station, like that. So we can identify the frequencies based on the functional groups. Of course, this is where people have made over the years. There are lots of stalwarts in NMR spectroscopy. Many of the applications have, over the years and years of the research experience, they have classified certain functional groups in the spectrum which comes from 0 to 10 or 15 ppm in proton, where these functional groups come. For example, this CH3 methyl group in the proton spectrum comes anywhere between, let us say, 1 to 2 ppm, or not 1, 0.5 to 2 ppm. So if you see in your NMR spectrum, there is a peak in this region. First, your focus for the analysis is, you should say, this molecule may have a CH3 group. That should be your conclusion. Start with an assumption to make assignment. It may so happen there may be a CH3 coming here. See, for example, OCH3, which comes between 3 to 4 ppm. So That is a further analysis because you have to say what is the neighboring group and everything. So by and large, functional groups, different protons, where it comes has been assigned. Similarly, I said OCH3, people know it comes anywhere between 3 to 4.5 ppm, depending upon adjacent groups attached to it. If I take, let us say, CH2 double bond C conjugated system, it can come anywhere between 5 to 6 ppm. I go to methane protons, CHC, CH protons, for example, conjugated methane can come anywhere between 6 to 9 ppm. Go to aromatic systems. Aromatic systems can come anywhere between 6 to 7 or 8 ppm. So like this, by and large, they have been classified over different ranges and different protons, different functional groups, where it comes, everything is classified. Okay, so when you take the NMR spectrum, you may have 10 peaks or 20 peaks, whatever, depending on your molecule. Use this idea before you start making the assignments of which peak correspond to which group. Start with this idea, start making the assignment. Then afterwards, you can refine it depending upon your neighboring groups, how neighboring groups is affecting the thought distribution of these molecules of this functional group like that. So this is the way you have to start analysis. The chemical ranges for different protons have been given like this. Of course, this is one chart I have taken from one of the books or site, but there are many like that. You don't have to worry. But the question is, it is not only for protons. For varieties of nuclei, various nuclei, such type of charts are available. For example, if I have a carbon-13 chemical shifts, remember carbon-13, if I see, the chemical shift varies from 0 to 300 ppm. It can go even beyond. In that case, again, if I see the carbon CH3 attached to halogen, it may come somewhere here. If I say I have to look for the CO group, it may be somewhere here. If I say I have to look for CH2 attached to oxygen, come somewhere here. Or if I want to see isocyanates, which comes in this region between, let us say, 130 to 150, like that. So if I want to see the aromatic comes somewhere around 130 to 150 ppm. These are all classifications for different nuclei. It basically gives you an idea how to start, where to start for the analysis. If I look for the ketones comes very downfield. Look at it. It comes around 200 ppm. Similarly, you can have range of chemicals or fluorine also. I don't want to go into the details. Different functional group. If I say fluorine attached to a methyl group, methane, it can come anywhere between. Of course, remember some of the chemical shifts or some nuclei can go to negative frequency, negative ppm. See here, with respect to CFCl3, when we measure, this can go to even minus 250 ppm, and this group comes somewhere between minus 50 to minus 200 ppm. Don't ever be under the impression chemical shifts are always, when expressed in ppm, always will be positive. It is true in most of the cases, but in some nuclei, and if you have a reference here like CFCl3, it can go such a way, it can even go to negative frequency. There are, depending upon the references used for different nuclei. So it can come from negative region, it can come to positive region, all those things are possible. So this is where the importance of the magnetic fields, how the spectrum comes, how to make the analysis. You have to make a judgment before making the analysis. Look at this one. This is a spectrum of a molecule, some molecule recorded 250 megahertz. See the importance. I explained to you what happened as you increase the field, how the spectrum dispersion takes place. If I give you the spectrum and ask you to analyze, how you will do it? Look at it. There is no resolution. Signal to isolation is very, very poor. So we will not be able to analyze very easily this type of spectrum at this frequency. Now, let us say you have the pleasure of using a high frequency spectrometer. You have an opportunity to record 600 megahertz, the same molecule, the same sample, same solution, which you have prepared in the NMRT, which I showed you in one of the classes. Take it and put it in a 600 megahertz spectrometer and then record the spectrum, see the range now. The same in the ppm scale, I'm not changing 3.4 to 5.4. It remains same. But look at the chemical shift dispersion here and the type of spectrum what you get here and here. Are you not getting better and better resolution here? Are you not getting the intensity much better here? This is what we were discussing all along. As you go to higher magnetic field, better resolution, and the sensitivity also goes as a power of 3 by 2 of the magnetic field. Look at this particular region which is highlighted here, 5.21 ppm. Look at this one. We had such a very good resolution you could see at 600 megahertz, which you don't see in 250 megahertz. So a spectrum appears different when you go to different fields. It is because the resolution will become better and we also get better signal to noise ratio. That is one thing. Sometimes it so happens the entirely spectrum appears different. For example, this is the molecule which is taken 3 protons here. So some attachment here we do not know what it is. A, B and C, there are 3 protons. This proton, this molecule, the proton spectrum taken at a 100 megahertz spectrometer appears like this. On the other hand, the same molecule, if we take the spectrum on a 600 megahertz spectrometer, this looks much better. Look at this, entirely a different spectrum. You don't get confused that you have made a mistake and this is not the spectrum of your molecule. No, same molecule. There is no mistake I have made. I have taken the same sample, recorded to 100 megahertz without getting confused. The same NMR tube, by putting the 600 megahertz spectrometer and recorded the spectrum, they appear different. Why it happens? This is what we have to understand when we go to analysis of the spectra. I will explain. This in NMR jargon is called strongly coupled spin system. At 100 megahertz, these 3 protons are strongly coupled among themselves. When you go to 600 megahertz, they become very weakly coupled and they get very easily separated out. And when they get separated out like this, it is easy for us to analyze. That's why the spectrum may appear entirely different at low and high fields. But does not mean your sample is wrong or don't get confused. You have to understand more about NMR, why it is happening at higher field, why it is happening in lower field. This concept we will discuss as we go higher. We will discuss these things. At the moment, you please remember this. Now I will tell you something about contribution to the total shielding. The total shielding chemical shift contributions comes because of basically 3 parameters. One is a diamagnetic contribution. I told you, sigma, the screening constant we can calculate with using that formula, Lamb's formula I explained to you. There are 3 contributions: diamagnetic contribution, paramagnetic contribution, and I because it is due to neighboring effect. Diamagnetic contribution comes because of s orbital. This contribution opposes the main magnetic field. This term opposes the main magnetic field. Paramagnetic contribution generally by p orbitals and other types of bonds. It adds to b naught. Remember, diametric contribution opposes the field. This adds to the field. And as far as the proton is concerned, this has little contribution. Whereas X nuclei, this has large contribution. What I mean by X nuclei? In NMR jargon, generally any nuclei apart from X, apart from proton, is called X nuclei. Whereas proton spectrum is generally studied all the time, maximum number of time. Maximum studies on proton. So any nuclei like carbon, silicon, nitrogen is considered to be X nuclei. So for X nuclei other than proton, this contribution becomes dominant. What is sigma? It comes because of the neighboring group. This can add or subtract depending upon the nature of the substituent. If I have an electron withdrawing group, it can withdraw electrons. If I add the electron donating group, it can give electron to that. As a consequence, the P can move anywhere in the spectrum. It can move to high field or it can move to low field. Remember, all these contributions are the total contribution for the chemical shift. Don't forget that. So with this idea, now we have to understand various effects are there to interpret the NMR spectrum, like steric effect, resonance effect, hyperconjugation. What happens if you attach a heavy atom for this, and delocalization aromatics, ring current effects. anisotropy effect, because of the anisotropy of the bonds. All these effects are present. Based on this, we can interpret the NMR spectrum and make assignments about the peaks which are coming at different regions of the spectrum. With this, now I will come back to I will tell you more about nuclear shielding and de-shielding, and few examples of how the spectrum can be interpreted based on where the peak is coming, etc. So what I'm going to do is I will stop here today. We'll come back next week in the next class. We'll continue further where we talk more about the interpretation and everything. I hope you understood. Today I have brought you the concept of chemical shift, especially conversion to ppm and to frequency, frequency to peak ppm, what it happens, and how the spectrum appear at low field, high field, the field dependence of the chemical shift. When expressed in ppm, what happens? When expressed in frequency, how the dispersion is there. All those things we understood. I hope you are all with me. We'll continue further in the next class.